Hey guys, welcome back to chapter 14. In this video, we are going to take what we learned about buffers and we're going to apply them to a problem calculating the pH. Best way to do that is just to dive in. So here's our problem. So we want to calculate the pH of a solution that is 0.1 molar acetic acid and 0.1 molar sodium acetate. So step one is going to be to write the balanced chemical equation for this, and then we're going to solve this very similar to everything we've been solving, and that's using an ice table. So our buffer is going to start out with the acetic acid. Acetic acid. And we're always going to mix that or react that with water. Let me move this over. Okay, so we're always going to react it with water, so I'm going to write that here, and then our acetic acid. So acetic acid is our acid, it's our proton donor. So we're going to have our acetate ion on the other side. And water is our base, so it's our proton acceptor. So we're going to have ion. Then we are going to solve this using an ice table because it's still a weak acid, weak base problem. To show you the one little wrinkle. So we're going to have our acetate, or sodium, our acetic acid. We still leave out water because it's a liquid. We have our acetate ion. And we've got our hydronium. This is an exponent. All right. So the wrinkle here, so buffers, there is a little wrinkle. When I go to fill in the initial concentrations, the products are not zero. So calculate the pH of a buffer that is 0.1 molar acetic acid. So the initial concentration of acetic acid is 0.1. But then we also have this other statement, 0.1 molar sodium acetate. So we also have some of this acetate ion present, and it tells us that that is also 0.1 molar. No mention of our no mention of our hydronium, so that is going to be 0. Okay. So wrinkle with buffer problems is that the products are not both 0. We do have a little bit of one of the products. Everything from here, though, is the same mindset, so change. Oh, well, our products aren't both 0, so how do we know which way it changes? Well, one of our products is 0. So the only way for this guy to go is to go up. So that's still going to be a plus X. And if hydronium is a plus X, this acetate ion is also going to be a plus X because they're on the same side of the reaction arrow, which means our reactant is going to go down. So at equilibrium, so the 0 still dictates the direction. At equilibrium, we have 0.1 minus X, 0.1 plus X, and X. All right, we're still going to write the equation. So we're starting with acetic acid, so it's going to be Ka. We've got products, so our acetate ion. Hydronium, and then our reactant, so again, just acetic acid. So I haven't given you the Ka value, but I want to talk about this other thing first, so let's just leave that as Ka for a moment. Now I'm going to plug in my concentrations at equilibrium, just like I've always done. So for the acetate ion, it's going to be 0.1 plus X, and then hydronium is just X, and on the bottom we have 0.1 minus X. Okay. So we're still going to use that the x is small assumption is true. So what we've been doing in the past is we can get rid of this x that's being subtracted on the bottom. Well, if subtracting by x isn't going to affect the outcome of this solution, why would adding the x affect the outcome? It's not. So we can do x is small twice because in both cases it's not going to affect that 0.1. It's not going to make it go up by very much. It's not going to make it go down by very much. So if we can ignore one of the x's, we can ignore both of them. So we're just going to do kind of a double x is small elimination here. So after we do the x is small elimination, we clean up that side of the equation, and we're left with 0.1 x over 0.1. Okay. So I just wanted to show you that kind of double elimination of the x is small. Now we can solve for Ka, get to the Ka value. Okay, so I never gave you the Ka value in this problem, but I will write it out to the side. All right. So the Ka for this equation is 1.8 times 10 to the negative fifth, so that's always going to be given. So we're going to bring this up here, and we're going to solve for x. So 1.8 times 10 to the negative fifth equals 0.1x over 0.1. Some of you may be able to see the algebra, and that's fine, but I'm going to still do it explicitly. So I'm going to multiply by 0.1. Those cancel. Whatever I do to the left side, I also have to do to the right side. So we're left with 0.1x. And then I'm going to multiply these two. So 1.8 times 10 to the negative fifth times 0.1. We get 1.8 times 10 to the negative sixth. And this is what I was saying. Now we're dividing by 0.1. And it brings us right back to where we started. All right, so we divide by 0.1. And we get that x equals 1.8 times 10 to the negative fifth. So what is that x? Remember that x was the concentration of hydronium at equilibrium. So we want to take this one more step because it is not asking us for x. It is asking us for pH. So that x value is the hydronium concentration. So pH is just the negative log of that. Negative log of 1.8 times 10 to the negative fifth. We get 4.75. So to summarize, we solved the pH of a buffer solution the same way that we would for a weak acid, weak base. So we wrote the balanced chemical equation. We used the ice table. The wrinkle here is that our initial value for our products does have a number in there. Now that I've done this problem longhand, now would be a great opportunity to tell you there's a shortcut. But I need to disclaimer. This shortcut only works for buffers. Do not try to do this shortcut for weak acids and weak bases. Only use this for buffers. Only for buffers. So because, or as long as we can assume that x is small, and it will be this chapter, but as long as the x is small, approximation is valid, we can use an equation known as the Henderson-Hasselbalch equation. Essentially, this is just a rearrangement of that Ka equation. If you'd like me to derive it for you, I can do that, or you can just take my word for it. But this is just a derivation or a rearrangement of that Ka equation. So the Henderson-Hasselbalch equation calculates the pH from pKa and initial concentrations of our buffer. Okay, so if we know pKa, we know initial concentrations of our buffer, we can use the Henderson-Hasselbalch equation. We also have to assume x is small is valid. It is. So here's our equation. pH equals pKa plus the log of the concentration of the base divided by the concentration of the acid. And that is, so for this, that is initial. So we don't have to do the ice table. This eliminates the need for an ice table. We can just simply plug in what it gives us to this equation, and we don't have to do ice tables for buffers. Now, the one thing I haven't addressed is this idea of pKa. So I introduced this a long time ago, but let me just remind you. So if pH equals negative log of this, pKa, very similarly, is just the negative log of Ka. So if we have the Ka value, we just simply take the negative log, and that's our pKa. Other than that, it's a pretty easy equation to use. Okay. A little bit more about the Henderson-Hasselbalch, and then I'll do an example in another video using this equation. So it's good as long as the x is small approximation is valid. Well, how do we know if the x is small approximation is valid other than the fact that Miss Maz told me it's valid? Here's the general rule of thumb. If the initial concentrations of the buffer are not very dilute, so that means that we've got things like 0.1 or 0.25, okay? Dilute would be like 0.00001 or 2.5 times 10 to the negative 6. So if they are very dilute, it may not work. If they're a little bit concentrated, then it's going to work better. And then as long as the Ka value is fairly small, so we've been working with things like times 10 to the negative 5th, times 10 to the negative 10th, things like that. So as long as both of those statements are true, then we can assume x is small is valid, and we can use the Henderson-Hasselbalch equation. In the next video, I'll work an example of Henderson-Hasselbalch, but I hope you guys found this helpful.